Welcome to this lecture in organometallic chemistry. In our previous lecture, we have looked into an important concept which is sigma donation and pi back donation that occurs between the ligand and the metal in organometallic compounds, and that results in a unique kind of reactivity for these transition metal compounds. These transition metal organometallic compounds thus show a variety of reactions which are unique to them, and we are at a point where we are trying to understand why does it happen or why is it so. And what we saw that it is the partial occupancy of their valence orbital which can lead to their acceptance of electrons or as well as back donation of electrons, leading to this unique sense of reactivity. And hence we came into a very important rule which is called 18 valence electron rule. This is a rule sort of used for guiding the stability of transition metal organometallic complexes, and that is often used as a definition of a stable organometallic transition metal organometallic compounds. And later we came to know that there are a large number of transition metal organometallic compounds which may obey this 18 valence electron rule, as well as some may violate the same. And in this lecture we try to understand the reason for compounds for doing so. And our approach in this discussion would be at looking at closely at this 18 valence electron rule, and also try to look at the metal ligand interaction from a molecular orbital standpoint, trying to see how does the metal orbitals really interact with the ligand orbitals in manifesting in their valence reactivity. So, with this we are going to start today's lecture on 18 valence electron rule and the classification of organometallic compounds. Now, usually it is said that thermodynamically stable transition metal complexes has 18 valence electrons. Stable transition metal complexes has 18 electron in valence shell. These complexes attain their 18 electron after combining with ligands and these 18 electrons are housed in five d orbitals, one s orbital and 3 p orbital. Overall, this leads to 9 orbitals having 18 valence electrons. Indeed, 18 valence electron compounds are extremely stable, and they are sort of inert towards many reactivity. With that in mind, let us look at a very stable compound which is ferrocene. Is a stable compound. It is often referred to as dicyclopentadienyl iodine. And it should have 18 valence electrons in its outer orbital. So, this leads to very important aspect of counting electron count or counting valence electrons. Electron counting is an important concept or important way of ascertaining the stability of complexes, and we should know how one count its valent electrons. There are two methods. One is ionic method of counting valence electron, and the other one is a neutral method. In ionic method, it is thought that this bis cyclopentadienyl iron is composed of two kinds of interaction, where you have two cyclopentadienyl anion each having 6 electrons. So, giving to 12 electron interacting with a iron 2 plus, which is 6 electron, leading to a total of 18 electron. Now, the other way of counting this is by the neutral method. In the neutral method, this 2 cyclopentadienyl ring is thought of as a 2 cyclopentadienyl radical, and they would bring about 10 valence electron, and iron is taken to be iron 0, hence 8 electron, and that gives a total of 18 electron. So, what is noteworthy over here, that immaterial of the method of counting the total valence electron, they sort of match independent of which method is used for counting the electrons. But one must be aware that if one uses ionic method, they should use ionic method all the way through, or if one uses neutral method, they should use neutral method all the way through, but they cannot halfway use a ionic method and then a neutral method and arrive at a right answer. So, you have to adapt to one formalism, either the ionic method or a neutral method in counting electrons. As far as I am concerned, I find neutral method to be more convenient to use, but that is simply just my personal preference. So, let us take a look at few other examples. Here is dodecacarbonyl manganese. So, we have Mn2CO10. The structure of this compound is with each manganese having 5 carbonyls, and there is a 1 manganese bond. So, in neutral method, five carbonyl will give 10 electron, manganese 0, 7 electron, 1 manganese bond giving 1 electron, and total of 18 electron. So, this obeys 18 electron count. Similarly, if we take diiron nonacarbonyl, the formula is and the structure of this compound is So, what we have here is 2 iron atoms, 3 carbonyls which are at the side, these are called terminal carbonyls, and 3 bridging carbonyls, these are called bridging carbonyls. So, again let us do the counting by neutral method. Three carbonyls, terminal carbonyls, 6 electrons, 3 bridging carbonyls, 3 electrons, Fe0, 8 electron, Fe, 1 electron, this gives a total of 18 electron per iron center. So, what we see is that ligands contribute differently as they bind. For example, when the CO is terminal, like situation like this, they contribute 2 electrons, 3 of them providing 6 electron, and when CO is bridging, as in the case over here, they provides a single electron. So, depending on how carbonyl binds to the metal, the number of electron it donates to the metal changes. Now, that brings back to an important topic of ligand classifications. So, how does ligands classify in transition metal organometallic chemistry? So, one thing one needs to know that certain ligands can have both neutral, positive and negative charges, and they may contribute electrons accordingly. For example, if we have metal alkyl, when the ligand is alkyl, aryl, halide, or in the neutral form, it contributes 1 electron. In the positive form, they do not really bind, and in the negative anion form, it contributes 2 electrons. Let us say if we look at other ligands, for example, olefins, carbon monoxide, phosphines. In the neutral form, they provide 2 electrons, they do not bind in the cationic and the anionic form. If there are ligands like pi, allyl type, NO, then in the neutral form they provide 3 electrons, in the positive form 2 electrons, in the negative form 4 electrons. So, this is a unique ligand which binds to the metal not only as a neutral entity, a positive entity or a negative entity, and provide different electrons. If there is diolefin, then in the neutral form it provides 4 electron. There are several examples of this, and I am going to just take some few representative anions. Let us say we have cyclopentadienyl, then in the neutral form 5 electrons and in the negative form 6 electrons. Let us go to an extreme example of cyclooctatetraene, which is C8H8 or C8H8 2 minus. So, in the neutral form it provides 8 electron, in anionic form it provides 10 electron. Now, let us look at the different electron donating abilities of these ligands that bind to transition metal. So, what we see, these ligands they can provide electrons all the way from 1 to 8 or even 2 to 10. So, that is a huge diversity in terms of the ligand being able to provide electrons to the metal. And also another important thing is that the ligand not only bind in the neutral or the negative state, but it also binds in a positive state or can bind in a positive state to the metal. Now, that is very counterintuitive, because metal itself usually are cationic in nature. So, a cationic metal interacting with cationic ligand is something which one would not initially sort of think right about. So, it is counterintuitive, but we have ligands in organometallic chemistry that can bind to the metal in all forms of states, and that is why it gives rise to some very important piece of chemistry. Now, let us take a look at the various classes of transition metal organometallic compounds, and these transition metal organometallic compounds are of 3 classes. Class 1 has 18 electron rule, not obeyed. That means they have valence electrons from 16, 17, 18, 19 and more. Now, we have class 2 where 18 valence electron rule not exceeded, and then their valence electron can have all numbers till up to 18. And last type are the class 3 types, which obey 18 valence electron rule, and they have only 18 valence electrons. So, what we see, this is class 2 where 18 valence electron rules are not exceeded. In their valence orbitals they have electron, they can have electrons which is 18, as well as they may have a number which is even lower than 18 like 16, 17, 18. Now, we have class 3 which has 18 valence electron rule obeyed, this for this class of compounds, and they have exactly 18 electrons in their valence shell. What is noteworthy is that our initial belief of 18 valence electron being the governing rule for transition metal organometallic chemistry is only one type of subset of the complexes that of total realm of organometallic compounds. There are 2 other classes equally existent, equally varied by their own right and merit beyond the 18 valence electron rules, and these were classes 2 and classes 1. Now, let us take a look at trying to understand how this classification happen, or what is the molecular level interaction happening between the metal and the ligand in forming these class 1, class 2, class 3 type complexes. So, in class 1 what we know that 18 electron rule is not valid. So, what is important to us is in trying to understand that how this 18 electron rule is not valid, but the compound can still be formed and compound can still exist. So, let us take a look at the interaction between ligand and metal for class 1 type of complexes in these transition metal organometallic compounds. So, for class 1, let us say we have metal orbital and we have now for the metal orbital there are let us say n minus 1 d levels d orbitals and this is the energy. So, there are 5 d orbitals. Now, above d will be the n s orbital and above s there will be 3 n p orbital. Now, these 9 orbital 5 plus 1 plus 3 would interact with ligand orbitals. Let us assume that these ligand orbitals are all sigma interacting. That means that these ligand orbitals will point towards the metal orbital along the axis, internuclear axis. And let us take a look at the simple octahedral complexes where we are looking at metal L6 octahedral kind of interaction. So, in such scenario there would be 6 ligand orbitals interacting with the sigma ligand orbitals interacting with these 9 metal orbitals. Now, of these if there are 6 sigma orbital, then the ligand orbital should interact with only 6 of the 9 metal orbitals. So, that means 3 of the 9 metal orbitals would not be interacting with this 6 sigma orbital. So, these 3 orbitals which do not interact are the ones which are not along the internuclear axis, but they are in between in the axis, and these are dx, dy and dz. So, 3 of these 6 orbitals would sort of not interact with these 6 of the ligand orbitals, and these are dxy, dyz, dzx. So, they sort of stay as non bonding. So, that leaves us with 2 of the d orbital, 1 of the s and 3 of the p orbitals interacting with the 6 of the ligand orbitals. So, they would interact 2 of these, 1 of that and 3 of that interact would give 6 bonding orbitals. And these are called A1G, EG, T1U. And these 3 dxy, dyz, dzx which does not interact are called T2G orbitals. Now, the way there are 6 bonding orbitals formed, that would result in 6 antibonding orbitals. 2 of the antibonding would be from the d type, and these would be the Eg star. So, Eg is over here, the bonding one, the antibonding is the Eg star. Then the Ns will give one orbital which is antibonding orbital called A1G star, and lastly 3 of the p orbitals would interact to give 3 sigma antibonding p orbitals called T1 U star. Now, what we see over here is that T2G is non-bonding, this is non-bonding, and EG star is the empty antibonding orbital, lowest empty antibonding orbital. Now, looking at this, one can arrive at the conditions for which the type 1 would be valid, and this difference in the energy is called delta 0 or the splitting energy. So, it says for class 1 type of complexes, delta 0 splitting is small and T2G is non-bonding, can be occupied 0 to 6 electron, and third EG star weakly antibonding, and can be occupied. So, what it says that electrons can be over here as well as over there. Now, if all of it is full, then how total we would get about 12 plus 6 18 plus 4 22 electrons, and if these are empty and these are full, then we should get about 12 6 into 2. So, overall what it means that for class 1 complexes there can be 12 to 22 valence electrons, and hence what we see that this explains why that class 1 type do not obey 18 valence electron rule, and for class 1 type there can be a valid 22 valence electron compound and still be stable. So, with that I will conclude today's lecture. What is interesting about today's lecture is we have constructed a molecular orbital correlation diagram looking at the orbital interaction of a metal center with that of a ligand center, how they come along and how they interact, how they give rise to the bonding and antibonding orbitals, and how the bonding and antibonding orbitals explain the total valence electron count and the stability of these complexes. So, we are going through a very exciting series of concepts we are developing, and in the next lecture what we are going to look in more detail about construction of molecular orbital diagrams for the class 2 and class 3 types of complexes and understand how they result in stability. So, with that I thank you for being with me in this class, and I look forward to being with you in the next class, where we take a much deeper look at this molecular orbital interaction for class 2 and class 3 type of complexes. I hope to look forward to being with you in the next class. Till then, goodbye and thank you.